Hi, in this video we will learn about combinations of functions. This gives us a method through which we can generate new functions out of old functions. So let's assume that we have two functions. Let f and b and g be two functions on R, meaning that the domain and the range is subset of R. Then we can define these new functions. We can define sum of f and g, sum of two functions. This is a function we denoted by f plus g. How does that work? So f plus g is a function. When you plug in an x, you will get the value of the function at f added to the value of the function at g. What happens for the domain? Domain of f plus g, so we have to be able to plug in x into f and into g. It means that x needs to be in the domain of both of these functions, and that means that the domain of the sum is the intersection of the domains. Well, that's one way. The other one is the difference of two functions. So f minus g. F minus g is a function defined this way, that if you want to evaluate at a point x, you evaluate f at x, you evaluate g at x, and then subtract them. And then the domain will be exactly same way. So domain of f minus g is, well, it should be in the intersection of the domain. So I will just write the intersection of domain of f and domain of g. The third one is, well, we can multiply two functions, and this is product of two functions. So f times g, this is the notation we use. So f times g, but what does that mean? What kind of function is that? Well, f times g at x is the value of f at x and value of the g at x multiplied. The domain, again, we have to be able to plug in x in both of these functions. So the domain would be, again, intersection of the domains. And the last one here we have is the quotient of two functions. Quotients of two functions. We have f over g. F over g is a function. When you wanted to find its value at x, you have to find value of f at x, value of g at x, and then divide fx by gx. What happens for the domain of the quotient is a little bit more interesting than the other ones, because if you divide, not only you need to, you see, x again needs to be in the domain of both f and g. So far is as before. But we have to be careful. We have to exclude the parts which makes the denominator 0. So exclude all x's in R, which makes gx 0. That is very obvious thing to exclude because, well, otherwise this doesn't make sense. Yes, you cannot put 0 in the denominator. So these are the 4 basic combinations of the functions. And we will do some examples for this. So example, first one is that, well, the table of values, a table of values of given, consider two functions f and g with the table of values given by, what is the table of value? Okay, x is 0, 1, 2, 3, and then we have f of x. So f at 0 is 1, 3, 0, 0, or it is for gx is 1, 2, 0, 3. Then the question says find these values, f plus g at 1. The second one says find f over g at 3. And find f minus g at 3. F minus g actually at 0. And the last one says that, okay, you have f plus g over f minus g. These are two functions. You divide them, and then you find the value of the function at 1. Okay, so here, I don't need to know the whole definition of whole formula for f and g. The definition says f plus g at any point is equal to f at that point, g at that point, and add them. So in other words, this is f at 1 plus g at 1, and we add them. By the table, f at 1 is 3, and g at 1 is 2. They add up to 5. How about f over g? At 3, it is the same thing as f at 3 divided by g at 3. F at 3 is 0. G at 3 is 3. 0 with 3 is 0. F minus g at 0. So f at 0 minus g at 0, which gives us 1 minus 1, and that's another 0 there. Here, or this one, we have f plus g. You see, this is a function, f plus g, divided by f minus g. This is a quotient. So we are evaluating at 1, so it means that we can evaluate each one at 1, and then find the quotient. But the numerator itself is a combination, so we can write it as f of 1 minus g of 1. Sorry, plus, the numerator is plus, and the denominator is f of 1 minus g of 1. And now we can plug in all values from the table. F of 1 is 3 plus g at 1 is 2. 3 minus 2, this is 5 over 1, which gives us just 5. Well, Another example would be that we have the whole function, the formula for the whole function, and then find the combination. So let f of x be x plus 1 over x minus 1, and g of x be x squared plus 2. Then find f plus g, find f times g, and find f over g. We can also ask for f minus g. Yeah. Well, this is a function. At any point x, it is equal to f of x plus g of x. And then this gives us x plus 1 over x minus 1 for f, plus x squared plus 2. I don't need to do anything else. Just that, leaving that is enough. We added two functions. Here at x, this is f at x times g at x. And then you multiply the formulas that we have here. X squared plus 2. Well, which gives us x plus 1 times x squared plus 2 over x minus 1. What happens for the fraction? Then this is x plus 1 over x minus 1, f of x over g of x. And that gives us x plus 1 over x minus 1 over times x squared plus 2. And then the subtraction will be basically the same thing for f minus x squared plus 2. Well, that's what you need to know about the combinations. And what we learned was that the combinations of two functions are new ways of generating new functions from old functions. And basically what happens is that all these algebraic operations, plus, minus, product, coefficient, are defined for the functions. And what they mean is that you evaluate each one by one and then apply the operation. And then we did some examples.